Okay,
See the
let's start.
Okay, yeah, thank you, Ian, for the warm introduction and the opportunity to speak here. Like Ian mentioned, my name is Alex Soloviev, and I'll be talking to you guys today about hydrodynamics and transport, soft pions and heavy ion collisions. And I'll break that title down for you over the coming slides. This is based on work that came out last month with my collaborators, postdoc Eduardo Grossi, who originally hailed from, well, he's from Florence and did his PhD there, and it went to Heidelberg to work in the group there, and now is a postdoc in Stony Brook with me. I'm Derek Tini, you guys probably know as well, well-established professor in Stony Brook, expert on nuclear theory and the like. And Funglita Jan is Derek's PhD student who's in his penultimate year now. So the way my talk is going to be structured is first I'm going to give some physical motivation, and then I'm going to talk about the hydrodynamic equations and the chiral limit, how we build it up, and it's kind of using a few tricks of the trade. Then primarily this talk will be kind of aimed at trying to compute transport coefficients in the chiral limit, and I'll describe how to do this, and we'll finish with some understanding, hopefully, of how critical scaling happens near the chiral phase transition. And if you guys have any questions, feel free to stop me, and yeah, hopefully I'll see that. Okay, so just like a lightning quick refresher on chiral symmetry breaking. In its simplest understanding, chiral phase transition is something that you see in QCD. It's characterized by the formation of the chiral condensate, which is just Q bar Q, so just fermionic condensate, and or quark, yeah, condensate made out of quarks, and it follows this kind of symmetry breaking pattern. So in the high temperature phase, you have this SU2 left cross SU2 right cross U1, and this gets broken down to just the vector part of SU2. And this symmetry is exact in the chiral limit. So when the quark mass vanishes, and we know from Goldstone's theorem that you should expect some sort of particles, some massless excitations. And in this case, we identify this with pions. But now, of course, in the real world, in QCD, the quark mass is non-zero, and the chiral symmetry is not exact. It's just approximate, kind of realized. And we can see that also by the fact that the pion mass is actually non-zero. But nevertheless, we can look at chiral symmetry and think about, is this actually visible? This symmetry breaking pattern, is this visible in nature? Can we see any signatures of this? And there's actually two things I want to talk about in the motivation. One is the really exciting thing that the lattice seems to indicate that there is such a transition and in fact it lives in the O4 universality class. So with the scaling exponents from the O4 universality class. There's also going to be, so this is still speculative, but in the future there's going to be these experiments which I'll describe, improvements to the Elise detector, where near the critical temperature, we expect some of the soft pions to escape, and these slow-moving pions might be able to provide some sort of window to the chiral dynamics, and that would be very exciting. So I'll give you guys some more details on this right now. So this is a plot from the hot QCD collaboration, and you can find the plot in this paper here. And this is how you can see the O4 scaling on the lattice. So this is a lattice simulation where we plot, and this is a plot from this lattice simulation. On the left side here, this is the chiral susceptibility plotted against the temperature for various pion masses, and the ratio here is the strange to the quark masses. Up and down are taken to be the same mass. And so just to orient yourself in this plot, because a lot is going on, this green line, this green line here is the physical, our physical world. So you see there's some sort of bump in the middle at some temperature. But now what you can do is you can do this Gedanken experiment and just like crank up, or rather crank down the pion mass. And what you see is, and start rerunning the simulation. So this brown one is with a pion mass of 55. You see that there's this enhancement of the chiral susceptibility. And the chiral susceptibility, like any susceptibility, once it gets very strongly peaked, you know that you're in the vicinity, or once it becomes divergent, you know that you're in the vicinity of a phase transition. So at least to me and to my eye, this looks very promising, that we do have some sort of soft notion here of this O4 scaling. And in fact, this collaboration also says how the scaling should go. So there's the quark mass here sitting in front with this power of 1 over delta minus 1, where delta is an O4 critical exponent. And f chi z is a scaling function, which is dependent only on z, which is this dimensionless variable, t times, so this is the reduced temperature, and the quark mass minus 1 over beta delta, which beta is also one of the coefficients of coming from O4, the O4 universality class. Okay. And what you can look at as well is the experimental status. So now switching to like the real world. So the lattice is something you do on a computer, but now maybe we can see something in a collider experiment. And then this is a plot from these gentlemen here with the archive number below. And basically this is the data here is plotted, and is the bold line is a fit from hydrodynamic models. And you see that the soft pions are very hard to fit to these hydrodynamic models, and you use these cascading resonance models to describe the production of pions, basically. And if you add more of these primary resonances, this only improves the situation marginally. So what I'm talking about specifically is here, this is the transverse momentum. And for small transverse momentum, you see that there's this excess of the ratio from what the data shows and what the modeling shows. So even though here it looks really nice, the data fits the model really well, in reality, it gets quite large. And so if we want to zero in and try to understand this region, so this is where the soft pions near the chiral phase transition would be apparent. What we would need to do is maybe think about looking at some experiments that can zoom in here, basically. And one such promising experiment is, or an upgrade at least, that'll allow some experiments to detect things, is this upgrade to the ITS detector at ELISE in CERN. So this ITS stands for Inner Tracking System, and what it's doing is it's allowing the experimentalist to see more low PT particles, low transverse momentum particles, and especially pions. And yeah, here's some plots from from one of their papers. So basically here, this is just the resolution, and this is the transverse momentum. And you can see that the resolution increases, basically, compared to what right now the standard is ITS2, and ITS3 is the future, and ITS3 here is just another one, basically. And so it'll increase by maybe, some amount, and people like to say that this will really improve our ability to resolve soft pions. And the kind of observables that you would have then is this multiplicity ratio of, these are all very standard things, of the charge to neutral pions, so how many neutral pions you have compared to how many charged pions you have. Yeah, pretty self-explanatory. Or you have some sort of correlation function between the charged pions. So that would be so we have some the way this work is described, I hope I've convinced you, is there's been some nice indication from the lattice that the chiral phase transition is in the O4 universality class. I'll then describe our work and extract some observable, indication of transport coefficients. And kind of in the future, the upgrade is slated to be whenever the long shutdown ends. So right now it says on their website November 2021, but who knows now with the current world situation, how much this will be delayed by. I've talked to some people in CERN and they say that it's basically 1-to-1. So however long CERN has been shut down now is how much it'll be delayed by in the future. For me, this seems optimistic. I don't know, but that's what they tell me. And yeah, so hopefully we'll be able to see some experimental signature and some more precise data coming out describing this near this phase transition. Okay, and now I want to talk about our model and the work that we did in this paper. And in order to do that, I need to set up kind of the physical picture. And so what I'm talking about is hydrodynamics and the chiral limit. So the theory that we have is QCD, and you have kind of, okay, these black lines are kind of the hydro modes. So we kind of think about all of your QCD degrees of freedom. So all the momentous scales that are below the pion mass are equilibrated, and there are these long wavelength excitations. And on top of that, you have these kind of momenta. So you have these waves, which are the superfluid modes here, which are on the scale of the pion mass living on top. And what we're interested in is, well, yeah. So as you can see, that at long distances, the effective theory should be just, QCD should be just hydrodynamics. So we'll think of it as pure hydrodynamics without any further considerations. But because we have this finite quark mass, we'll also have these extra excitations. And what we're interested in is how these extra excitations affect the hydro background. So specifically, how do the superfluid modes, these red lines here, how do they affect the overall hydrodynamics and particular the transport coefficients?
Alex, can I ask something?
Yeah.
So in this picture, you're away from the phase transition.
Yeah, we're in the broken phase.
You're in the broken. It's okay. Thanks.
Oh, okay. Yeah, no problem. Oh, I didn't say. Yeah, so we're below TC, and all the statements I'll be making today are below TC. We're going to take the condensate to be constant, and I'll talk about where our theory is valid, but we're basically we're really close to TC, but we're below it. And in future work, we'll relax this assumption and actually have a dynamical variation of our condensate as well. Okay, and kind of jumping ahead to what we would expect to see. So the kind of point of this whole paper is to compute the correction to the transport coefficients that are due to the quark mass. And what we're looking for is these three transport coefficients. There's the bulk viscosity, the shear viscosity, and the isovector conductivity. And basically you have the bare, just focusing on the bulk viscosity, you'll have the bare bulk viscosity, which is being corrected by a pion mass. And there's the correction that we're computing is this is zeta 1. And for the shear viscosity is the other way. Notice that of the signs, so the bulk viscosity is expected to see an enhancement near the phase transition, whereas the shear viscosity is expected to decrease near the phase transition. And this is somewhat standard. I've seen this in lots of different talks and different circumstances. So it's nice that we're fitting into kind of the standard picture. And what's interesting with the isovector conductivity is actually that instead of the correction coming at the next order, so a linear order in the pion mass, it actually comes in as 1 over m pi. And kind of the way that I understand this is above, so if you take the limit and the pion mass goes to 0, the bulk viscosity and the shear viscosity return to their usual QCD values, right? That's our background, is the background hydrodynamics. But there is no isovector to conduct basically in QCD, at least in the approximation we're working on in. So as a result, the isobector conductivity kind of is divergent there at the critical temperature. And also it's worthwhile to point out that this expansion is non-analytic in quark mass. We'll be computing hydro loops because the pion mass is proportional to the square root of the quark mass. Okay, so.
Alex, where did you get this from? M pi is proportional to square root mq?
So in chiral perturbation theory, the pion mass is given as the sum of the up and the down divided by f pi, right? And so it's proportional to the lightest quark masses, right? So divided by the f pi, right?
Okay.
And then that's mass. Huh?
You get it from the chiral perturbation theory.
Yeah.
Okay.
Yeah. Okay.
I was thinking you're getting it somehow from the O4 critical point or something.
No. This is just from the chiral perturbation theory. Okay, and so now just to give like a sketch of superfluid hydrodynamics. Originally, this was started by Son in this paper here, and there's been some future work with Son and Stefanov as well that I'll reference. But the basic ingredients in the model are you have some conserved quantities like the energy momentum tensor and an approximately conserved axial current. There you have also the phase of the chiral condensate and the pion field. So this is the pion field phi, and the phase is just it's denoted by U, which is written in terms of the Pauli spin matrices and the pion fields here in this kind of O4 language. And you also have the variables. So you have your usual temperature, velocity, and the chemical potentials, mu left and mu right, because you have SU2 left, SU2 right. And also you have this Josephson constraint, which relates the phase, so the phase of the chiral condensate, to the chemical potential. And we also have this mass term because we're in the broken phase and we want our Goldstone fields to actually decay. So we actually want to describe something a bit more physical. And so as a first start, what you do is you set up ideal chiral hydrodynamics. And the general way you do this is you write down an action. This is in a curved background. You have the pressure of the hydrodynamic pressure, basically, and the superfluid microscopic degrees of freedom sit here, and they're coupled in through the metric, basically. And and the superfluid microscopic degrees of freedom are described by this Lagrangian. And you see here, this is what you would standardly get from chiral perturbation theory. Here you have a kinetic term. This is d mu u d mu dagger. And this is, oh, actually this is a typo. This should be the spatial projection. So you have a term, so we're working at finite temperature, and this should be the time-like projection, and this should be the spatial projection, such that f squared over chi is the pion velocity. And we also have an explicit mass breaking term here as well to break the symmetry. And ultimately, we will work in linear order in phi, where we just linearize the phase. So we write u is equal to 2I phi, and then we just linearize this, and we can compute the equations of motion, and so on from there.
Alex, this action that you wrote down should also be understood as giving the equations of motion for u and t, or I should put it separately?
What is t? For the temperature.
The temperature and the velocity.
Yeah. So when you compute the energy momentum tensor, you'll get the conservation of the energy momentum tensor, and that will kind of be your equation for t.
Okay.
Yeah.
You will get the full superfluid t mu.
Yeah.
I see.
Or you'll get the full theory t mu nu, and then there'll also be a contribution from the superfluid. And I'll talk about how this gets reapportioned within the standard hydro story. So you basically get corrections to your energy density and pressure from the hydro, and you just call that the new energy density. You redefine your energy density and pressure.
And how many quarks do you have? 3?
So we don't have any. We're working with pions.
Okay.
So yeah,
so,
you have
but your U would be, depending on if you just have pi's.
Yeah. In this case, it's linearized, so it's basically like there's the one.
Okay. So it's just some number.
Yeah. Okay, and I should also describe there's one extra constraint that we need to think about, which is the Josephson constraint, which relates. We have this chemical potential which we need to relate to our phase. And just like a quick derivation, this is coming from Son. In Son's language as well, he works with a Hamiltonian and with Poisson brackets, whereas our language is more in the Lagrangian language. But just borrowing his discussion of the Josephson constraint is really nice. So the whole O4 field, sigma, can be written in polar representation like this. So little sigma here is the chiral condensate, and U is the phase. So in general, in the course of this talk, we take little sigma to be constant, and we don't worry about it, and we're just interested in the dynamics of the phase. But we know that if you have this dynamical sigma, that it needs to be stationary with respect to the Hamiltonian, and here this is the two chemical potentials. Furthermore, what you know is how the Poisson bracket of sigma transforms with Q, and it goes like this, and you have the other transformation property with the right guy. And what you find basically in the linearized regime is exactly that the phase comes out to be exactly equal to the axial chemical potential. So it's the axial chemical potential is in this particular combination of your left and your right charges, of your left and right chemical potentials. And in the linearized form, what you find is, you see a lot of things. So the 2I phi, only the derivative remains, and the U dagger cancels it out. So you just have dt phi is equal to minus the axial chemical potential. So it's quite a simple relation in the linearized regime.
Alex,
Yep.
So this assumption of stationarity is something that you put on top, or is it? It should be consistent with the equations of motion, I guess, but it's something you're putting on top.
It's something that needs to be consistent with your equations of motion. Yeah.
Okay, I see.
Yeah. Okay. And then what you can do is you just do the standard computation for your energy momentum tensor and also for your current. So first I'll focus on the energy momentum tensor. And you see that you have the standard ideal hydro form. And then you also have this piece which is only in the phi variable, so only in written in terms of the phase. And so this, what I would call the kind of decomposition, which I write down here as well, this is kind of the ideal hydro part, and this is the superfluid part. But what you see is that the energy, this is kind of sly, because the energy density and the pressure aren't just the standard hydro energy density and pressure. What you find is that the energy density and pressure are actually redefined. So this is what you would write down. This is the typical energy density that you would have in your normal hydro if you didn't have any of these superfluid microscopic degrees of freedom. And what you find is that the energy density can be redefined if you take this variation with respect to the superfluid, Lagrangian. And likewise, the pressure is just redefined in this way as well. So in this way, you're no longer working with your usual hydrodynamics. There's this kind of, in a sense, kind of this redefinition of these energy densities and pressure.
Alex,
Yep.
The mass of the pion is then absorbed in the energy density and pressure?
Yeah, yeah. And it'll come out, so I haven't described the equations of motion, but you'll also see it explicitly there. But yeah, at the level of the energy momentum tensor, it's like not, there's, you only have it in the energy density and the pressure.
Okay, thanks.
Yeah. Okay, and then you can also compute the axial current from the action that I described before, and you'll have two pieces as well. If you had just everything was the usual, you would just have this normal piece coming out, n times u mu. U mu is the forward velocity as well, yeah. And you also have this now, the superfluid piece, which comes out, which is proportional to the axial chemical potential as well. And this current is partially conserved. So the energy momentum tensor is fully conserved with respect to the background metric e to mu nu. And the current is partially conserved, so you have this explicit breaking term on the right-hand side. Okay, that's all well and good. But right now, I've been talking about ideal hydro and ideal superfluidity. But now we want to add dissipation because the world that we live in is relatively viscous. And especially the chiral phase transition, we know that viscosity is an important effect. And so what we want to do is we want to be very careful about how we choose dissipation. We want to be sure we're describing the real world physics. So we want to have this choice of dissipative terms such that we have positive entropy production. And what we do is it's a relatively standard way of adding dissipation. You take your energy momentum tensor that we were describing before. This is the ideal part. And you add a dissipation tensor, and also for the left and right currents, which make up the axial current, you'll also add a dissipation, this Q mu left, Q mu right. It's kind of like a dissipation current. And just like what you would do standardly as well, this pi, you can decompose into a shear and bulk part. So the shear is traceless. And the bulk term is just given in terms of the spatial projector. And also we have to allow for viscous corrections to the Josephson constraint to make sure everything is kosher. And that just comes in the form of adding a dissipative axial chemical potential to our Josephson constraint. And we'll also be working just kind of standard as well in the Landau frame. So everything, all of these dissipative terms contracted with the forward velocity are, they all vanish.
Alex, here I'm a bit confused actually, because usually in the Landau frame, you cannot guarantee both. Usually what you do, you just either you choose u dot pi is equal to 0 or you choose u dot q is equal to 0. The u dot q is equal to 0 is often called the Eckart frame. And so I'm a bit confused here because you can get, I think, this thermoelectric effect, which is comes from but you won't get it if you probably enforce u dot q equal to 0 also.
Yeah. I don't know about that. So are you saying that these two conditions together are inconsistent somehow, or?
No, not inconsistent, but you are basically amounts to putting thermoelectric effect to 0. So usually, see, there are 4 conditions, right? U dot pi is equal to 0, and you need, so essentially, so I think what usually it amounts to say that U is the eigenvector of T mu, right? That is the Landau condition. If you say that, so you say the U is the energy current. That's the meaning of it. Now, if you say the U is the, like the charge current, then you get, that's a different definition of U. Out of equilibrium, the charge current velocity and the energy current velocity need not be the same. So what Landau does is to define the U as the energy current velocity, and then you can have the thermoelectric coefficient will sit in J. Right? Now, if you say that all these things vanish, then you won't get any thermoelectric effect at all.
Right, yeah. I guess we don't have that then.
Okay.
Okay. No, thanks for the observation. I'll think about this a little more. But yeah, just okay. Yeah, modulo this last point. The story continues with the entropy production. So the entropy is defined as you would expect. This is also this kind of redefined entropy at some temperature. This is the energy density and pressure that's redefined. And you have the chemical potentials, the left and the right. And yeah, I'm using the shorthand where mu left dot NL is just the trace and divided by the fundamental normalization. And okay, then what we do is you can compute the entropy production. This is also relatively standard. We assume this partially conserved axial current conservation and partially, yeah, I already said conserved there. Okay, I said conserved twice. It's an ATM machine. And also we contract U nu with the energy momentum conservation. So we use basically these two current conservations. And we can write down a formula for the entropy production. So we see that the ideal part is conserved. So, and these are all dissipative corrections. So this is the entropy current, and these are also the mu left and mu right currents. And what focusing, oh yeah, also there's one term here that I haven't mentioned. This is this theta s, and this is what's known as what we define as the superfluid expansion scalar. So it looks like a scalar. I mean, it has some index for the SU2, but it's a scalar all the same in the Lorentz sense. And you see it takes this form, so it's a derivative of the phase plus this explicit breaking term here. And it's hitting this dissipative chemical potential. It'll make its appearance every so often. And it's kind of the expansion parameter of your superfluid, if you will. Okay, and so I can focus on individual terms at a time. And I'll just take you through first the entropy production. It's really straightforward. If you want positive entropy production in the tensor sector, you find that there's only one such structure, and that's the shear tensor. That's pi mu nu, and to the order of derivatives that we're working on, this is just the shear tensor. And it has this coefficient with the sign to make sure the entropy production is positive. And so as a result, we take eta 0 to be greater than 0. So we see here the pi mu nu comes from here, and we have a minus sign in front. Conventionally, you define the shear tensor with a minus sign. And as a result, we require this coefficient to be larger than 0. And we can do this for also the scalar sector. What you find is you have two possible structures. There's this, the bulk kind of term is also, it's all in here basically. You have this is one coefficient, which is zeta. There's the divergence of the fore velocity, and you also have, again, this chemical potential dotted with a superfluid velocity. And you also can have a scalar term coming in from here. So you have some sort of, it looks like you have some overspecification, basically, because this dissipative axial chemical potential also can have such a nabla.u term. And what you see is actually, if you write everything out explicitly, these two terms should have the same coefficient sitting in front. They basically add up. And finally, this mu axial dissipative can also have a superfluid piece. And these coefficients then, so the way that it's not really obvious to see in this, how it's written here in the entropy conservation, but the quantity which emerges is one that looks like this. You have pi nabla.u plus the axial dissipative term times the superfluid piece. has to be larger than 0. So this is the piece that actually appears on the right-hand side of the entropy production. And what this requires is a slightly more involved a number of constraints. So this zeta 0 needs to be larger than 0. Zeta 2 needs to also be larger than 0. And then this particular combination of zeta 0 and zeta 2 needs to be larger than zeta 1 squared and u a squared.
So it appears that you have taken some matrix and its positivity condition. That's what these
Yeah.
conditions look like.
Basically.
Alex?
Yeah.
So I have some basic question here because I'm a little lost. So you said that you will explain where the equations of motion come from. So can you say whether I'm understanding correctly? So from the Lagrangian gives you the equation of motion of the phi, of the u, sorry, or rather the phi variable, which is e to the power 2i phi is u, right? And then from the energy momentum conservation and the charge conservation, you get the equations for T, the chemical potential, and the velocity field. Is it correct description?
Yeah. So that's the ideal part. Yeah. And then we add dissipation.
Yeah. Okay. Yeah. So yeah. So, but still, your equations, the equation of motion for phi, which is log of u, essentially, that comes from the same action, right?
Yeah. But what I'm doing now is I'm constructing all of the terms that are consistent that we can add to our equation of motion, and the way that are dissipative. So we're trying to do this in a consistent way, coming from the thermodynamics.
I see. So I think what you're trying to say that that the Josephson junction condition, sorry, the Josephson condition, right? That should be interpreted as the equation of motion for phi, or so I'm a bit confused about what is how do you get the equation of motion for phi in presence of dissipation? That actually I'm not completely.
I'll get to that. I'm not there yet. So this is just the discussion of how dissipative entropy production should work.
So right now you're only considering the equations of motion for the standard hydro with influence of the phi.
Yeah. With the ideal, the input is the ideal equations from hydro and from the superfluid.
Okay. So you're just looking into the ideal equations, and then you're saying what is the effect you will have if you have dissipation. I see. And then this zeta 1, zeta 2, these are essentially an expansion in MPi, like the MPi. So zeta 2 is what?
Yeah, this is a little unfortunate, but no, these are just coefficients. Yeah.
Okay. This is nothing to do with the first. Because some days ago you had. Okay, I see. Okay.
Good. Okay. Yeah, and because it's the story is the same in the vector and axial sector. There you only get two conditions. So the coefficient there and the axial conductivity needs to be larger than 0. And sorry. These are the bulk viscosities basically. But okay. Sorry, I'm a little tired. It is a little early in the morning for me. But basically, long story short, what we find from this entropy production story is you have this whole theory, this hydrodynamic superfluid theory has 3 transport coefficients, which is the shear viscosity, the bulk viscosity, and the isobector conductivity. You get these 2 pion damping parameters. So this is this zeta 2 coming from the scalar sector, and this axial conductivity here. And you also have this coupling parameter between the normal and the pion sector, which is this zeta 1. And just kind of the interpretation of this whole thing is you can then write down the equations of motion in a really nice way. So what we're doing basically is you take the pion equation of motion, which is just the superfluid expansion. This is this theta s that I mentioned before. And this is equal to some chemical potential, and this is the how do I say this? This is the phi that I've been computing, and this is kind of the normal chemical potential. And if you had normal kinetic theory or standard hydrodynamics, you would get a similar equation for the hard pions or the hard hadronic states. So it'd be given like this in terms of the number of the left and the number of the right. And there would also be this kind of balancing of the chemical potentials here. So kind of what the entropy production, what this whole analysis kind of was indicative was the way we're coupling these two theories, these two sectors, is through their chemical potentials. And kind of the equations, the dissipation, what it wants to do is it wants to relax the system into having chemical equilibration, basically. And okay, now we can start getting into adding these dissipative terms into the equations of motion. And this is, so now we are safe in the knowledge of all of our transport coefficients are the right sign. And so this is the gradient expansion following Son and Stefanov in 2002. So the partially conserved axial current equation is given here. So you have the J0 and the Ji, and this is the explicit breaking term. And what we're going to do is we're going to add these dissipative corrections to the and some noise to drive the ideal equations and the Josephson constraints. So this Ji, just the spatial part of the current, normally is given in terms of this phase. But now what we do is we add a bit of the axial chemical potential to it with this dissipation. So this is a gradient in the axial chemical potential. And this is some noise term. And likewise, the Josephson constraint, this is the ideal piece that I mentioned before in the linearized regime. And what we do is we add some gradients of the phase. And there's two such terms that we can add, or that Son and Stefanov added. One is like Nablus squared, and the other one is kind of like a mass term. And what we found through our and just to finish with Son and Stefanov, what they say is, okay, if we want to actually generate some dissipation, we want the noise terms to have vanishing mean, whereas we want the variance to be given by these transports, by these dissipative corrections. So this is this dissipation, which is due for the vector, and this is for the scalar, the zeta 2. And kind of our small contribution in this whole story is that we find that this correction that you add to the Josephson constraint, that's dissipative, actually it's not two transport coefficients, it's one fewer. So we just have the zeta 2 sitting here. So that kind of simplifies the theory. It's like a little small improvement, but you know, it's nice that we were able to find this. And that just goes to show the power of this entropy production method analysis, because then you really can see terms that you don't overcount how many transport coefficients you need. Okay, and basically, long story short, that was kind of a long aside for what is really an easy thing that I think everybody is capable of doing, is you have these linearized equations with dissipation. So what you find using this dissipative partially conserved axial current and the Josephson constraint, you find a dissipative wave equation. So long story short, the framework was kind of overkill for what our purposes are in this work, but like in the future, this will be handy. But what we find is basically this ideal part is just the ideal wave equation, as you can see, plus this explicit breaking term. And then we have this dissipative part and fluctuation dissipation relation. We also have to have some noise terms on the right-hand side. And you can see that this is like Nablus squared. So this is like the gradient squared time derivative, and this is just a time derivative with these particular coefficients in front.
Alex,
yep.
So this probably answers the question that I was asking, right? The first term, the ideal parts, comes from the action, I guess, right? If I'm understanding.
Yes. Yeah.
But in general, if you have a U also, then a non-trivial flow, then I think del T square should be U dot del, and That's what I understand, right? This u dot, it should be, the del T is simply the projection of the derivative in the fluid direction.
You mean this dt here?
Yeah.
Yeah. But we don't have flow basically.
Okay, yeah. Okay.
Because it's also, you can think about like if you're near the chiral phase transition and you're producing pions, they'll have very little transverse momentum. So you're kind of like, well, you can just think of them as basically stationary. There's no like flow of them.
Okay, thank you.
Yeah. Okay, and then just like as a mini tutorial, how do you go about solving this stuff? You need to compute the symmetrized propagator. So this is this object here that I call G5 phi. It's the propagator of the phi phi's. And you have these indices A, B. These are kind of the SU2 indices. And you find a pretty standard form. So you have a pole as well. And this gamma Q is the attenuation. And what you see, okay, yeah, I think the only thing that's not defined on the slide is this chi A. This is just a coefficient of the time variable. And this is the axial susceptibility. And yeah, what you find is the quasi-particle energy is given in this way. So omega Q squared, which appears here explicitly, is given by the pion velocity squared, and then Q is the momentum squared, and M is the mass. And the pion velocity, which was, I guess, introduced by Pozharsky and Titgat in this paper, is given by F squared over chi A. And this is something that you can just read off from the action directly. I mean, here you can also see it's just F squared. In the wave equation, it's just F squared over chi A. And the attenuation is similarly, you can decompose it into two pieces. So there's one piece which goes like momentum squared, and the other one which goes like the mass squared, the pole mass squared. And with these two coefficients, and these two coefficients are given in our entropy analysis, in this entropy production analysis, in this particular way, in this particular combination. So there's this axial conductivity and the zeta 2. And likewise here, there's this zeta 2 and some constants in front. Okay, and now this is a really standard slide. This is for the Kubo formula, where basically what's pictured here is how you compute the shear viscosity, or kind of what you're interested in. So the shear viscosity is defined in this way. You're computing TXY, and properly normalized as well. The isovector conductivity is just the the vector current operator combination. And the bulk viscosity is given in terms of this O bulk, which I'll talk about on the next slide. The operators which appear then are so first you have the TXY is just given by gradient of phi in the y direction. The vector current is given like this as well. It's all very simple. And this O bulk operator is basically the trace of the energy momentum tensor, which is nice, basically. Rather than computing just the diagonal pieces, you have this nice compact form, and it is a little neater in the computation, and it has a little bit better properties in the hydrodynamic limit. And so here what appears is the speed of sound squared, and beta here is the inverse temperature. So everything can be written nicely. You then go through and evaluate these integrals. But what you find first is that, let me just tell you about the physical objects, things that you can actually measure. So the integrals depend on these thermodynamic properties of the soft pions. So the pole mass, for instance, is given by F squared times M squared. And the pion velocity, again, is given by F squared over chi, and the speed of sound squared is speed of sound squared. And all of these objects on the right-hand side, and this is just the speed of sound squared, can be determined from Euclidean measurements on the lattice in principle. So these are all accessible through lattice computations in principle. And also the two damping transport coefficients, dA and dmp, are what what the integrals depend on. Okay. Also, what makes an appearance is this thermal velocity and the thermal mass. So this is this little squiggle, the tilde at the top, is denotes thermal. So v tilde squared is the velocity squared minus the second derivative with respect to temperature. I forgot the 2 up here as well. And likewise for the pion mass, there's also this temperature correction here. And finally, you have this dimensionless ratio, which parameterizes the attenuation. So the attenuation, remember, is given by dA q squared plus dmp and p squared. So this dimensionless ratio is with a proper factor of f sitting in front. It's just given by the square root. And what's interesting, so this is an observation of Derrick's and his collaborators, Juan Torres Francon and Banglida Yan, which is still in preparation. But in chiral perturbation theory, you can do the one loop computation, and what you find is actually this ratio is exactly 4/3, which is kind of surprising. But yeah, so this in principle is something calculable and kind of a nice dimensionless ratio to think about the results in. And yeah, lo and behold, after doing these computations, which are a little involved, what you find is the transport coefficients have been modified. And you see here that there's, these are the transport coefficients as promised. There's the, I'm not going to say bare, the physical bare parameter, plus a correction, which always goes like m. So this is the pion mass m. And you have some terms here. So first I'm going to say a few words about this, the phys under thing, which is that these expressions, so like the bulk viscosity gets renormalized. So you have the bare parameter evaluated at some scale lambda. I guess this correction, which is kind of funny. So you see here that this is a divergent piece. It's linearly divergent in lambda, and this combination is a little amusing because in the so if you just plug in some numbers, CS squared is like 1/3, and if you have a conformal fluid, and V tilde, if you are at 0 temperature, then V tilde equals V, right? So this is just the thermal. It has the thermal contribution, and so what you find is that if you're really working at 0 temperature with a conformal fluid, the bulk viscosity doesn't actually get any contribution, doesn't get renormalized, whereas the shear viscosity always will. So there's just this lambda that sits here. But yeah, then you have, I can talk a little bit about these contributions. So you see here that you have the thermal masses appear, the speed of sound squared. These are the ratios R. And yeah, the bulk viscosity is a little complicated to understand, but what you see in the shear viscosity, for instance, or even better in the isovector conductivity, is the correction, besides some numbers in front and some constants to make things dimensionless, they all depend just on this ratio of the two attenuations, of the two coefficients of the attenuations. So it's like a really nice and simple thing, but also maybe it's really hard to understand what this physically implies. Yeah, okay, before I get to that, there's always two ways to skin a cat, as we say in New York. And another way that you can actually reach the same answer is you can set up this hydro-kinetic approach, which is also detailed in our paper. And just to give a quick sketch, what you work instead is with the pion distribution function, f pi. And then you have this kind of Boltzmann-like equation where on the right-hand side, you have this relaxation time. It's a term which is like approximates the collision kernel in a relaxation time kind of way. And this h which appears is the effective Hamiltonian, where q's are the momenta, and v squared is the pion velocity. So it looks what you would kind of expect. This is kind of like p squared plus m squared, m pole mass squared. But what you have to be careful about is that you're in a co-moving fluid, right? So you have to find the frame where you're moving with the fluid, and so the metric actually is a little different. It's u mu u nu, and there's the pion velocity appearing, and then there's the spatial projection operator as well. And yeah, this f pi, you can see the equilibrium distribution function, which is basically this term here, but if you pull out the omega q, is t over omega q. And what you do is you can then use the standard machinery of kinetic theory, and after you go on shell, so when you set h equals 0, so when p squared plus m squared equals 0, you can then compute the energy momentum tensor, and from there you can extract these corrections, which we've done as well, so you can check that both methods give you the same solution. So this is just another way of approaching the same problem. Okay, but that was a little aside, hopefully not too distracting. So what I want to talk about now is how do we understand these results near the critical temperature? So to answer this, what we're going to do is we're going to follow some arguments that Son and Stefanov made. They've done all of this at the start of the millennium, basically. What we first will note is that near TC, this ratio goes roughly to 0 because the mass term is basically unimportant compared to the momenta. Next, what you note is that the pion damping rate, or what we call gamma pi, should begin scaling like the condensate damping rate, gamma sigma, when you're at the momentum scale where you're at this, where the momentum is roughly similar as the screening mass of the condensate. So the condensate damping should be going like the pion damping, and that goes, since the mass isn't so important, as you get close to the temperature, to the critical temperature, you just get this kind of scaling of dA q squared. And another result is that you expect that you have this dynamic universality scaling of your condensate. So when gamma sigma is roughly the screening mass to the power of z near the critical temperature, where z is this is a critical exponent, which is just the dimension over 2. And since the screening mass is kind of like a it's kind of like a correlation. What's the right word? Well, okay, it scales like the temperature to this critical exponent nu. What you're able to do is you're able to extract the exact scaling of your damping coefficient. So you see that dA should be given with this combination precisely, which just follows from these arguments above. And likewise, you can go through all of the other components, and you can make similar scaling arguments. But what you need to know, or keep in mind, is that we're really close to TC, but we're not close enough that we have to take sigma fluctuations into account. So that's a relatively narrow statement. So we're not talking about a whole range of temperatures. We're talking about a small band. And it's precisely where we can come close to TC, but where we can't neglect these fluctuations of the condensate are when the screening mass becomes at the same order as the two masses, basically, or when the quark mass scales in this way, basically. When the quark mass reaches these kinds of temperatures of given in this way. So 3 nu minus beta. These are the two critical exponents. And what this means practically is that this analysis breaks down whenever your temperature is already hitting basically the quark mass to the power of 1/2, roughly. I mean, we get this number, it's whenever the reduced temperature is basically the square root of the quark mass. But yeah, long story short, what you can do is you can apply all of these approximations, and you see when R goes to 0, the structure becomes a little bit more transparent. So here, for the shear viscosity, you see immediately that you have a minus sign, and there's the mass. And in the isovector conductivity as well, you have this 1/m as promised. And the bulk viscosity, you still see that there's these, so we've taken the limit where R goes to 0 first, just to simplify all of these expressions. And you see that you still have this kind of structure of 1/3 minus CS squared that you saw, and also the renormalized physical parameter, bare parameter. And yeah, what you can find then is when you plug in all of these scaling of these transport coefficients, what you see is that the bulk viscosity, so you have this, the bare piece, has this kind of particular temperature dependence. So you have, now these are just, this is just, we assume that the speed of sound doesn't really scale, and the quark mass, well, it doesn't change at all, of course, and then this is just some constant sitting in front. And so the temperature is goes like beta over 2 minus 4. So what we find is that the bulk viscosity near the phase transition, so as T goes to 0, is rapidly changing and getting, well, quite large. The
so
shear viscosity.
Alex, how did you get these numbers? Did you use the O4 critical exponents?
Yes, yeah, oh yeah, I should have mentioned, yeah, we're using the O4 parameters, yeah. The O4 values for the scaling, for the betas, nus, and deltas, yeah, for the exponents, yeah. So this is assuming that the chiral phase transition really is, if we really believe what the lattice is telling us, and we take these values as input, this is the kind of scaling you would expect near the chiral phase transition. Likewise, you can do the same thing for the shear viscosity, and you find it's a much more mild growth, or yeah. So it goes like, yeah, the temperature to a much smaller number than the bulk viscosity, and the charge diffusion just kind of goes to 0, which is what you would kind of expect, because above TC you don't really expect there to be much charge that's diffused. But yeah, the kind of future direction of this project is to understand how including sigma fluctuations, or the fluctuations in the chiral condensate, will change all of this. So when, and we can maybe also think about moving away from the linearized regime. So there are some plans to maybe, well, eventually we want to use some real hydrocode and simulate what happens when we add these superfluid modes, whether this changes something about what you see, like for instance, you can compute multiplicities of particles that come out, and or you can also compute like these V2s and V4s and see if proximity to the chiral phase transition changes the expectation of these observables. So what you expect to see in experiment. So with that, I thank you guys for your attention, and I'm open to questions. There were a lot of questions already, but I'm very happy to answer some more.
Thanks, Alex, for this very nice talk.
Thanks.
So as Alex said, let us take some questions now.
No questions, I guess. There were a lot of questions during the talk, so I think it's I've been thoroughly examined.
Okay, then let me ask something very basic actually.
Oh, sure.
So normally what happens is that you can add this the dissipative terms, whatever you like, it is consistent with the gradient expansion, and you have some definition of u and t, right, as variables, u, t, and mu. You give some definitions of these variables using Landau frame, Eckart frame, whatever. And then you simply compute an entropy current. And that entropy current does the following, that if you require the positivity of the divergence of the entropy current, it puts some constraints on the non-dissipative transport coefficients that you added higher order in derivatives, right? And it only gives inequalities for the dissipative transport coefficients.
Yes.
So that's a normal story. So, so now in your talk, there were many, I think, some coefficients which were determined as a function of t and mu, but I guess these were non-dissipative, right?
Yeah, they were non-dissipative. That's right.
Okay. Yeah, that's the usual story. That's what I wanted to know.
Yeah, it gets kind of complicated, but you basically, you're always using the lowest order equations to compute the dissipative corrections, basically. So yeah, then if you have dependence on T and V, you will have them at the dissipative order as well.
Yeah, okay. Right. Okay, so yeah, so I don't think I have any further question. So yeah, so let's thank Alex again for this very nice talk and also getting up so early in the morning.
I'm ready to go back to sleep, to be honest.
Okay, so see you then again next week, and all of you. And next week we are not having a talk because it will be during strings, so we have cancelled the talk. So the talk afterwards will be a talk on statistical mechanics by Rakibur Rahman, who is a faculty in Bangladesh in Dhaka University, and also he is now in Potsdam on sabbatical. So we will have a talk on statistical mechanics. So see you all on July 9, I guess. Yes. Okay, so have a nice day, all of you. Thanks for being here. And
Thanks,
bye.
Alex.
Bye.